Getting back on more with the alternating current theory, as you know, is sinusoidal current. We have our sine and our cosine, which are reciprocals of each other, basically. They are 90 degrees apart on your classic unit circle, which hopefully if you've taken at least high school trigonometry, you'll have some vague memory of, hopefully. So, and this funny looking little W, that's not a W, that's the Greek letter omega in lowercase. Just like omega in uppercase, this that is for ohms. We use lowercase omega to represent radian, not radiant like the sun has rays that go out. No, just radian. Like, say we have pi radians in 180 degrees or what have you, the trigonometry radian term. Radian frequency is frequency which exists over time. So omega equals 2 pi, which gives you 360 degrees, times your frequency. Frequency is how many cycles per second. So sine omega t equals cosine omega t minus 90 degrees. And the reverse of that is cosine omega t equals sine omega t plus 90 degrees. So cosine leads sine by 90 degrees. See, there's sine, which starts at the zero crossing, and there's cosine, which starts where x is equal to 0 and y is equal to 1. And sine starts where x and y are both 0. So sine of a negative omega t value is equal to negative sine times omega t. And cosine of negative omega t will always give you a positive value. Cosine always gives you a positive value, but sine might give you a negative value. So your old, I don't know if these are trigonometric identities specifically, but they kind of relate, and they, as we play around with sine functions and capacitors versus inductors, and we start getting into that kind of stuff. So your time domain notation, when you're starting out with alternating current, so is A, which is your peak value, times your sinusoidal function. Remember SOHCAHTOA? SOHCAHTOA, S-O-H, sine is opposite over hypotenuse. I just use a sine button on my calculator, my TI-89. And then omega t, which is omega 2 pi times your frequency. And t is your time in seconds. But for the homework problems that we had, we just left this t, whatever time you want. And then plus or minus, that's a plus or minus there. And then that's the Greek letter theta. Theta is your degrees, plus or minus on the y-axis when x is 0. So here we have an example that theta on the left equals 0. There's 0 degrees. But then we have a lagging or theta negative value when our x is equal to, say, for example, 1. And that's when our sine wave crosses the x-axis at, then our angle is going to be negative. And then if our sine wave crosses the x-axis at x equals, say, for example, -1, then we say the angle is leading and is positive. And that's just how that works. So you remember resistor and capacitors and inductors, so we get to play with all of them, and these RC and RL filters. And we have cutoff for corner or 3 decibel or 3 dB point frequencies. So what these are also known as is high pass and low pass filters. So we have RC, resistor capacitor, the F sub C, or the cutoff frequency, is 1 over 2 pi RC, the reciprocal of 2 pi times the resistor value times the capacitor value. And there's 2 different ways to make them. Now and we look again at RL equivalence of them here, then we have our corner frequency R over 2 pi L is how we determine what frequency, how many cycles per second it will start to either allow more signal, more voltage to get through, or will start to diminish how much voltage get through. Either low frequencies will get through or high frequencies will get through in this case. So resistance, inductance, capacitance. Now if you think about these just from the diagrams here, well, if you have a voltage source here and then you want to take the voltage across this capacitor, if you have a really low frequency, basically close to say DC or a constant current, then the voltage is going to just drop across this resistor and then out across this capacitor. Well, that's going to act like an open circuit. So that means if it's an open circuit, the capacitor may as well not be there. So at a really low frequency, we're just going to take the voltage across the resistor, and it's going to be about the same as your voltage source. But if we switch places of resistor and capacitor at a really low frequency, then so this is what we call a low pass filter. Low frequencies pass through, they ignore the capacitor. But then at a low frequency, then we have, it's going to hit this capacitor and say, hey, we're exceeding that 5 tau value. If you remember the 5 tau for how much time it takes for a capacitor to charge and discharge, if you have a really low frequency, lower than our 5 tau, then okay, it's going to block current flow from getting through here. So that means, okay, but as the frequency goes up and up and up to be greater than or exceed our 5 tau, well then okay, current's going to get through. There's going to be this resistor here in parallel with where we're taking a measurement of voltage or feeding the rest of some circuit downstream from this resistor, and it's going to be a high pass filter. Likewise with so here we have a low pass, and here we have a high pass filter. Low frequencies pass through, high frequencies pass through, according to the frequency determined by this formula for both circuits. There's RC and RL filters. RL filters, same idea really. If you remember, with an inductor at a low frequency, it's going to act like a short. So this is also a low pass filter, and as the frequency goes up and up higher and higher, it's going to do the opposite of what a capacitor does, and it's going to overload because the magnetic field builds up, and that's what stores the current in a capacitor. It's going to get saturated. So a high frequency is going to restrict the current flow. It's going to choke down on it, and it's not going to pass through. So that means this acts like this, essentially. And same over here, but we have a reactive component that's going to act like this, but the opposite. So, but it's pretty rare when you're actually building these circuits or taking apart components to actually see an inductor, because they tend to be expensive and really finicky to deal with. So you're probably going to see RC capacitors in practice more often. gain. I mentioned gain in dB briefly a while ago. So gain, let's say we have, and this is a model for any one of those four filters that we just talked about. It can talk about their impedances. So your gain, and it's measured in dB decibels. Yes, just like sound decibels, but this is electrical gain, is V out, how many volts you get out, divided by V in. It's simply a ratio. So here's V out across that resistor or capacitor or inductor, divided by your V in. At V out over V in, which is also equal to your first impedance, the one going across the top, divided by the sum of the two impedances. And it's also equal to C2 over the sum of the impedances, apparently. So, and then that will get you V out over V in ratio, but to get it converted to decibels, you have 20 times log base 10 of that V out over V in ratio. And that is, well, this 20 log is for a more or less an ideal case, which is, but you're not going to get that every single time the ideal case. That's the limit of what we covered in the class I took. So V out over V in is, again, here's with this J omega L and R plus J omega L. And we'll get into that J in complex algebra. And see here we have V out over V in. It goes up, and there's kind of this steep part here, and it levels off. Or here we have our decibel is going to go increasingly up. There's our cutoff or corner frequency, and then it's going to level out. Use this with the filter analysis. So let's talk a little bit more about impedance here. Impedance, we called that Z. Z in for measured V in and V out. So Z is, think of impedance like the AC form of resistance. Remember R equals V over I in Ohm's law? Well, Z, our impedance, equals V in over I. It's just, and these little bars, these funny bars here, that means magnitude. That means ignore the angle. We talked about theta and the angle earlier, but if we ignore the angle, then this just means you just take these bars and you just take the magnitude, the absolute value of V over I. And then we have our I equals V over R because of the algebraic property of such a configuration. Voltage across resistor, resistor value, input voltage, peak values, and there's an example. Feel free to pause the video if you want and look at that. Something else with AC voltage is that it can be writing on top of a DC voltage. So we have RMS, or root mean square voltage, which is our DC squared plus RMS squared voltage. So let's talk about, there's this relationship between AC voltage and the square root of 2, which I won't go over here, but it's covered here. So let's say if we have 6 volts DC here on our oscilloscope screen, this is voltage over time. It's 6 volts, and on top of that, it goes up here and it peaks at 7.5 volts. So it peaks at 1.5 volts higher. So that's 7.5 volts minus 6 volts. So the RMS square root of the RMS voltage is equal to 6 squared plus 1.5 over square root of 2 squared. So see, 1.5. There's a relationship between peak and RMS voltage. You divide it by peak by the square root of 2. And that will give you your DC squared plus AC RMS squared. You might see that now and then.